Hi everyone, welcome back to ECE484. Sorry I was a minute late there, some technical issues. Okay, so let's continue where we were. So what did we talk about last class? So we're doing review, chapter 2, we're basically done, so we'll finish it in the first 5 minutes today. As I said before, it was a quick review, so I mean, of course you do a full course on introductory control, analog control, signals and systems and so on, and you cover much of this material, if not all of it. And so this was sort of a quick and dirty review, and hopefully it at least refreshed some ideas in your mind. Okay, so what we talked about, last time we finished our discussion on the frequency response of a stable LTI system. And then we mentioned that it's kind of useful to graphically represent the frequency response, and that's what a Bode plot is typically, right? And so Bode plot is just magnitude versus frequency and phase versus frequency, except that the units are decibels for the magnitude, and the horizontal axis, or the x-axis, is typically written in log scale. Okay, then we moved on to model reduction, which is sort of a practical issue, right? I mean, if you have a complicated model, sometimes it's hard to design a controller for it, and so it would be nice, given that you're going to use feedback, and feedback, gives you robustness to sort of model uncertainty, it's nice to simplify the model when you can. And so what we argued was that sometimes a system naturally, or the physics of a system kind of decomposes, you can decompose it into like a fast part, think of the electrical part, and a slower part, which is often the mechanical part. And they kind of operate on different time scales. And in terms of a transfer function, that manifests itself in the way that certain poles and zeros are further away from the imaginary axis than others, okay? And what we argued in that last class is that we can replace those sort of fast poles and zeros with their steady state gain if we're looking at things like step responses or other low frequency inputs. Okay. Then we started talking about kind of the central problem of control, which is, tracking. In other words, having the output of a system track a desired output asymptotically in the presence of disturbances and model uncertainty and so on. Okay, and we started off with kind of the simplest version of this problem, or often the most useful. That is step tracking, right? A lot of control problems can be thought of as get to a certain value, maintain your system at a certain value, and have that value change over time. So that's a step tracking problem. And what we argued, essentially using the final value theorem, was that if you've got a stable closed loop system, so feedback stability, and the controller plant combo, C times P, has a pole at S equal to 0, then you get perfect step tracking for any reference, which is a step, right? And the size of the step doesn't matter, you still get perfect step tracking. Now, someone asked me after the class yesterday, well, how can you have stability, right? If the plant and the controller have a pole at S equal to 0, doesn't that mean that they're unstable? And the answer is yes, of course, absolutely. That is totally true. If, let's say the controller has the pole at S equal to 0, then the controller on its own is unstable, right? Bounded inputs to the controller can produce bounded outputs. However, the whole point of using feedback is that in feedback, the closed loop system can be stabilized, right? Even though the individual components are unstable. Okay, so what we want to do now, and we started doing last time, is to sort of generalize the discussion we had about step tracking to arbitrary reference signals, right? Steps are an important type of reference signal, no doubt, but sometimes you want to track other types of signals. So for example, in a power system, the energy system that we use, the electrical network, we want to keep the phase or the oscillations at 60 hertz, right? And so you need a controller that's going to try to keep those oscillations at 60 hertz. So there you're tracking a sinusoid. Okay, and that led us to this statement below, which I didn't write last time, but I started writing, but I didn't actually complete it. And this was the so-called internal model principle of control. Okay, so let's read it, and then I'll try to interpret it. You should keep in mind the intuition of the step, right? Okay, so the internal model principle says, so assume that the plant is strictly proper, the controller is proper, and that the feedback loop is I/O stable. Okay? This notion of strictly proper, this is sort of a technicality. This is just to make sure that the loop is well defined, right? Let's just make sure that there's no kind of undefined transfer functions. All right, so the statement says that if the controller and the plant together contains an internal model of the unstable part of the reference, then we get asymptotic tracking. Okay, so I've written that in a sort of a way which is maybe not very formal, because what do I mean by the unstable part of R? Right? What exactly does that mean? So let's kind of go through the statement and see what happens. So what it's saying is the following. Say that R of S, so this is the Laplace transform of the reference, so you have the numerator of R over the denominator of R, right? So that's the Laplace transform of the reference. Let's factor the denominator of the reference's Laplace transform so that we have one polynomial, which we'll call stable, having all its roots with negative real part, times another polynomial having all its roots with real part greater than or equal to 0. So I'm going to factor the denominator. Into these two polynomials, d minus and d plus. So here, so d minus R of S has all its roots with real part of S less than 0, right? So that's where the minus comes from, right? The real part is negative. D plus R of S has all its roots with real part of S. Okay? And that's the part, what's what we're going to call the unstable part of the reference. So to remind you of what this looked like for a step. So e.g., in our example from last class, our reference signal was this. Right? That's our step input. So in this case, we would say that the numerator of R of S is just the constant R naught. The stable part of R is anything in the denominator with roots less than 0. In this case, there are none, so it's just going to be the number 1. And d plus R of S are all the roots of S with real part greater than or equal to 0. In this case, it's just S. Okay? So in this case, I would say that this is the unstable part of R in terms of the theorem. Okay, so what the internal model principle says that the internal model principle says that if the controller and the plant, okay, so the controller will be some numerator over some denominator, the plant will be some numerator over some denominator. What we need is that that product contain embedded in it the unstable part of R. So it says that if this C times P has the form, so whatever, some numerator over some denominator, but it has to have a copy, an internal model of R of S. Right? So just like in the case of step tracking, we needed an integrator. More generally, we just need the unstable part of R. So this is what we'll call the internal model. Of the reference. So if your controller and the plant look like that, and you have I/O stability, then you get perfect tracking. In other words, the steady state tracking error is equal to 0. for that reference. Okay? And so how would you go about convincing yourself that this is true? Use the exact same argument that we used for the step. And so what we'd like to do to argue that the steady state tracking error is 0 is again use the final value theorem. So let's check what would happen if we were to use the final value theorem. So let's look. So what we need to do to check for the final value theorem is, like, as we said before, I need to check that this quantity, s times E of s, if that thing has no poles with non-negative real part, then this limit will equal the limit of this as s goes to 0. Okay, so let's check this quantity. Right, so there's s, and then the transfer function from r to e times r. Right, so that's E of s there. Okay. Remember that we're writing our reference in a particular way, so let's do that. I'll come back to the transfer function in a second. This will be the transfer function, but the reference, remember, we wrote as nr of s over d minus d plus r of s. Okay? And so for the last thing to do is fill in this transfer function. So what I'll do is I'll put it over a common denominator, just as we did, earlier. But remember that the internal model principle says that our controllers times plant, so the denominator of that product has to look like that. So when I do put it over a common denominator, what will I get? I will get in the numerator here, I'll get d of s. D plus r of s. And in the denominator, I'll get the usual characteristic polynomial. All right? And so now look what happens. Again, we get this cancellation. And now look at the quantity that's left. By IO stability, the characteristic polynomial has no bad roots. Oops, so here's a question. So the question is, to clarify, n of s and d of s, referring to this thing here, are the numerator and denominator of the product CMP, whereas these, so no. So, I mean, I guess one way you could think of this is that I'm saying that this quantity here equals numerator of controller, numerator of plant, over denominator of controller. The usual thing, denominator of plant, right? But it has a special form. So I've just kind of combined these two to call that n of s. And in the denominator, what I've done is I've said, well, whatever this product is, the internal model principle says it must have a copy of the bad part of the reference, or the unstable part of the reference. Okay? So I've just, this becomes n of s. This denominator, whatever it ends up being, is, if you're using the internal model principle, it has to have a copy of the reference and then whatever's left over. Okay, so sorry, back to what we were saying. So this guy has no bad roots by the assumption of IO stability. This guy is no bad roots because that's the stable part of the reference. And so, good. And so this thing has no bad roots. Final value theorem applies. And when we take the limit as s goes to 0, this s here is going to go to 0. And the whole thing will go to 0 because, of course, this has no bad roots. So it has no roots at s equal to 0. So it won't cancel this. And so when you take the limit as s goes to 0, the steady state tracking is 0. So just point out, no bad roots. So by final value theorem, ESS equals 0. All right. And so integral control for steps is just a special case of that. Okay, so that's the end of our review. We're going to move on now to Chapter 3. So Chapter 3 this course is about digital control, but as I said at the beginning, there's 2 points of view you can take to digital control, right? In our introductory example, you can take the point of view of the plant, and that led us to this notion of emulation, right? Design continuous time controllers, then discretize. And so this chapter that we're going to talk about now is sort of an emulation. It's going to help us in emulation. It's a way to design continuous time controllers that in the next chapter we'll learn how to discretize. So, chapter 3. Pole placement using polynomials. Okay, so we're going to have our standard unity feedback system, and so let's just draw it. Oops. All right, so we've got R, E, C, P, Y, D, and U. All right, so our standard unity feedback system. And we want to design, we're going to design controllers in this chapter. And so I just want to give the high-level idea before we get into the nitty-gritty. So the idea in this chapter. And this is something I mentioned when we were talking about transient response. So the idea is that given P and some specs, convert the specs into a good, quote-unquote, region of the complex plane. Which, by the way, is something that I asked you to do in problem set 2, right? In problem set 2, I asked you to kind of do this sort of thing. And then design C of S so that all the, let's call it closed loop poles. What do I mean by closed loop poles? I mean the roots of the characteristic polynomial. Right? That's what when I say closed loop poles, that's what I'm talking about. I'm talking about the roots of that polynomial which determines input-output stability. Are in the good region. Okay, so that's the basic idea. So let's do an example to motivate what will come. Suppose that I give you a kind of a simplest or a simple control design problem. I give you a plant. It admittedly a bit artificial in the sense that I just made up this plant. It's not based on a physical system. But suppose I give you this plant. And the spec is just closed loop stability. All right, so you got to do something because this plant on its own is not stable. If it were stable already, then you don't need to do anything. So the poles of the plant are approximately negative 0.75 and 0.88 plus or minus j 0.75. Okay, so These guys have positive real parts. So the plant on its own in open loop is not stable. So you can't just solve this problem by doing nothing. You got to do something. Okay, so the poles, there's one at negative 0.75. But then you've got these guys over here. So 0.8 and 0.75. Okay, so you've taken your introductory control course. You've probably seen that PID dominates industrial control, right? It's a control architecture which is very popular in industry. So without knowing much else, you say, let's try PID, right? Why not? So let me remind you of what a PID controller looked like. It's got a proportional part, the transfer function, plus an integral part, plus a derivative part. Now, I'll be generous here to make your life even better. That derivative part, you see, if I write this over a common denominator, the controller is improper. So the controller is unstable. So sometimes you don't like unstable controllers, so it's very common in practice. Also, it's not implementable, right? It's common in practice to kind of, quote unquote, roll off the derivative term. Right? Because you can't perfectly implement a derivative term anyway. It's non-causal. So it's very common to do this. And as an aside, in what sense is this approximately a derivative term? Well, let's look at the Bode plot. If I were to plot the Bode plot of a perfect differentiator, it would look like this. Right? The magnitude Bode plot. I'll just draw the magnitude. What does the Bode plot of this term look like, which is not s? It's now s divided by tau d of s plus 1. Well, it's going to basically be equal to the derivative, the ideal derivative up to a certain point. And then at some point, it will cut off. Okay, so this is sort of our practical differentiator. And what's the frequency at which it cuts off? That depends on the parameter tau d. Okay, so this is our PID controller with it's implementable, right? It doesn't have this ideal differentiator, it has a real, something you can actually implement. Okay, so we have now these parameters. So I want to rewrite this controller just because the point here is to argue that this controller is not going to work to stabilize. So let's imagine now I put everything over a common denominator in the controller and I just collect all the terms. I argue that this controller looks like the following. It looks like a second order polynomial in the numerator, over a second order polynomial in the denominator, but it has a pole at the origin because of the integral, right? The integrator gives you a pole at the origin. Okay, so the expressions for G2, G1, G0, and F1, they're not important. Just if you want, you can derive them yourself, but I'm not doing anything fancy there. Just write the controller as numerator over denominator, and you'll get something like that. Okay, so the question now then, in terms of this design problem, is pick the G's. The question is, why do we need to roll off the differentiator? So if you may remember, when we were talking about Bibo stability, that every improper transfer function is not stable, right? So the integrator is improper, And so it's unstable. So on its own, it's unstable, and you can see what it does, right? It amplifies high-frequency noise, right? So if there's any noise in your system and you have an ideal differentiator, it's going to amplify that noise. So that's one issue, it's unstable. The second issue is you can't implement the ideal differentiator. It's unimplementable because it's non-causal, right? So if I give you a function of time, and I want to take its exact derivative, I need to know what it will do in the future, because remember, derivative is a limit from two directions, right? So ideal differentiation requires future information. So it's not implementable. You can't implement that in real time because right now, whatever information I've acquired, I don't know what will happen in the future. So I can't implement an ideal differentiator. It's unimplementable. It's non-causal. Need future information. So of course, what you do is you approximate it when you implement it, but it's common in PID control to just accept the fact that I can't implement a differentiator perfectly, and then cut it off at a certain frequency. And that has the nice benefit is that it caps the amplification of high frequency noise, right? So notice that my approximation to the differentiator, there's sort of like a maximum gain that I'm going to get for high frequency noise. Whereas my ideal differentiator, there's no cap. It's going to keep amplifying higher and higher frequency noise. Okay? So it's a kind of a practical thing that you see in any sort of PID control, right? The ideal differentiator is not implementable. So yeah. I don't know if that makes sense. So anyway, this is a nice way to do it, right? Because you now have an extra design parameter, this tau d, that you can play around with, an extra knob you can tune to get your controller to do its thing. Yeah, so these are practical issues related to PID, which maybe you probably may have seen in your third-year course. In any case, so the idea here then again is I want to see if this PID controller can stabilize the plane. So let's check the characteristic polynomial. Okay, so there's the plant. So it's going to be the denominator of the plant times the denominator of the controller plus the numerator of the plant times the numerator of the controller. If you do all that, you get a messy expression, but let's write it down. So nothing fancy going on here. Okay, so here's our characteristic polynomial. So remember, the only spec here is stability. So what I need to do now is I need to pick the gains, the g's and the f's, so that this polynomial has all of its roots with negative real part, right? And once I pick the f's and the g's, I can go back and translate them into proportional gain, integral gain, derivative gain, and this tau d parameter. But we have a problem here. Look at this polynomial. What you may have seen when you were doing Routh-Hurwitz in third year is that a necessary condition for a polynomial to have all its poles or roots with negative real part is that the signs of the coefficients have to be equal, right? If the signs aren't all equal, then it's not stable. It's not Hurwitz. If they are all equal, they may or may not be. You can't conclude anything, but it's definitely necessary. Like at a bare minimum, the signs of all the coefficients have to be the same. So in this case, positive, so +1. So that means that this guy has to be positive. So we immediately get the constraint that f1 has to be greater than 1. That's at a bare minimum. I mean, it's not guaranteed that's going to stabilize the system, but at a bare minimum, we need f1 greater than 1. But over here, we get the constraint that f1 has to be less than 0. So we have this conflicting constraint on the f1 parameter in our controller. We need it to be greater than 1, but at the same time less than 0. So it's not possible, which means that there's no choice of PID gains, which will result in feedback stability. There is no choice. Of controller gain that results in feedback stability. And so the idea then of that example is to hopefully motivate why we need more complicated controllers. Okay? Coincidentally, for second order plants, you don't need more than PID to solve this problem. But once you get to third order, like in this example, right, third order plant, PID doesn't always solve the problem. Okay, so again, the idea here is that given the plant and some specs, convert the specs into a good region of the complex plane, and then design the controller so that all the closed loop poles are in the good region. So in this example we did, the good region was just the open left half plane, right? Stability was the only spec. But in general, we're going to have other specs like percentage overshoot, settling time, and so on. So let's convert those specs into a good region. So section 3.1. Converting design specs into desired pole locations. Oops, that's not what I want to do. Sorry about that. Okay, so we're talking about a unity feedback system. And so the characteristic polynomial is denominator of plant, denominator of controller, plus numerator of plant, numerator of controller. Okay? For our design purposes, we are going to assume that that polynomial is second order. Remember that in chapter 2, we derived all these equations for settling time and all that stuff for a second order underdamped system. And so what we're going to do to motivate these equations, we're going to assume that this polynomial is second order. So for our design, approach, we'll assume, and I want to emphasize that this is an assumption that we'll have to deal with at some point. We're going to assume that pi of s equals our second order polynomial from chapter 2, and that it's that the system is underdamped. So second order underdamped. Okay? Because this is what will get all our equations for percentage overshoot, settling time, and all that. Okay? But of course, a real system, most real systems, especially in closed loop systems, are not going to be second order. So we need to do something, we need to take care of we have to be careful in our design to make sure that this is a reasonable assumption. So what we'll do then, and then we're going to have to justify the approximation. Let's see. The approximation in our final design. Okay, so we'll have to make sure that, that our design actually makes this approximation reasonable. Okay, so I remind you that for this guy here, this polynomial, we have a certain picture for its root locations. And it was like this. So So those were the poles. So negative zeta omega n was this guy. This was 1 minus zeta squared, the imaginary part. And this angle was theta. Okay, so just this is the stuff that we did in chapter 2. Okay, so we're assuming that our system is second order underdamped, so its poles look like that, and we're going to translate specs into desired pole locations, or acceptable pole locations. So we'll start with settling time. Okay, so the spec is a maximum settling time. For a step response, right? So the settling time of our step response should be some less than or equal to some maximum value. So in step response. And of course, it's a reasonable spec. The settling time is greater than 0. Okay? Now, since from chapter 2, we derive that the settling time is 4 over the negative real part, so in other words, the absolute value of the real part of the poles, we can convert this spec into a constraint on the real part of the poles. The spec is equivalent to zeta omega n greater than or equal to 4 over Ts max. Okay, and again, look at the picture above. This is negative the real part of the poles. Okay, so if you have a settling time spec, our good region in the complex plane will look like this. Okay, so I'll draw a line here. Where is that line? That line is exactly negative 4. Well, let's draw it this way. That distance there is 4 over Ts max. Okay, and so as you get smaller and smaller settling time, that purple line is going to move further and further to the left. And so our good region here is all this stuff here. So I'll call that complex plane sub G for good. Okay, so there's our good region for the settling time spec. So in this equation, it's a set of points in the complex plane where the real part of S is less than or equal to 4 over Ts max. Okay, so settling time spec pulls sufficiently far to the left. Phase margin. Oh, sorry, no, overshoot is what I want to do. I'm not going to do phase margin. Overshoot. We're going to do the same sort of thing. You're going to be given a maximum overshoot, and then you want to turn that into an allowable region in the S-plane. So our given spec is that the overshoot, remember how far the step response goes above its steady state value, is less than some maximum value. And I remind you that when we write our percentages here, it's a number between 0 and 1. In this case, we don't allow 0 or 1 in the case of the spec, or this discussion. Okay, so we do the same thing before, as we said before. The overshoot depended on zeta, the damping ratio, and the damping ratio determines the angle of the poles, the argument of the poles. And so we're going to convert this spec into a constraint on the angle, or the argument of the poles. So since percentage overshoot equals, this is from chapter 2, right, so this is our equation from chapter 2, and zeta equals cos theta. I'm going to just scroll a bit to show you again where theta was. Theta is this angle, and so the argument of the poles is pi minus theta, and then negative pi minus theta, right? Okay, so because of that, and because of that, this is equivalent to the spec that is. A maximum angle, right? You know, as the damping ratio gets bigger and bigger, your overshoot goes down. You can think of it as like friction in the system, right? There's more and more friction, so you get less and less overshoot. And so what's happening is your poles are getting closer and closer to the real axis. So that angle theta is getting smaller. So the constraint on overshoot becomes kind of a maximum angle constraint on this theta. And what is that maximum? Well, you can just write it in terms of the given spec. So again, there's nothing too fancy going on here, just some basic manipulations. So it's the arc cos of the following. And that pi is not the characteristic polynomial, that is 3.14, so on. Okay, so the spec, you're given overshoot max, plug it into the formula, you get a maximum angle, and that now gives you an allowable region in the complex plane. So let's draw the picture. Imaginary part of S. Let's draw it like this way. So you're going to get a cone, right? And the angle that this cone makes is theta max. Okay? So we want all of our poles to be in this kind of sideways cone. So in this case, that will be our good part of the complex plane. Okay? And so if I want to write down a formula, or not a formula, but rather an expression for the good region, it would be that the absolute value of the angle of these s's should be greater than or equal to pi. minus theta max. Okay, and if you have both specs, well, then you intersect them, right? You intersect this cone with the thing we saw for settling time, which is sort of a left half plane, and then you get this cone with its top chopped off. Okay? And so that becomes where you want your closed loop poles, i.e. the roots of the characteristic polynomial. Okay, so there you can also do the same sort of thing with time to peak and phase margin. I won't go over it in class. It's in the notes. You can take a look. Okay, so let's get to our design problem. So again, the idea is we do what we just talked about. You convert your specs into a desired region in the S-plane, and then we put our poles there, or closed loop poles. Okay, so we'll do, the plant, general, is going to look like the numerator of the plant over the denominator of the plant, and it's going to have order n. Okay, so there we have our plant, nth order plant. So in the example that we started at the start of this chapter, n was equal to 3. Okay, our controller will be mth order. All right, and so just like for the PID controller, I'll use G's for the numerator. And F's for the numerator, or denominator. Okay, so I realize that I could always just get rid of this Fm and absorb it into the other coefficients. I could always, without loss of generality, make that denominator have a leading coefficient of 1. For our design equations, it's just convenient to keep that as in that form. Okay, so that's the reason that I wrote the controller that way, but not the plant. All right, and of course the F's and the G's are our controller gains. Right, so notice this contains PID controllers. It also contains basically any linear time invariant controller of order m. Okay, and so then we get pi of s. And that the degree of pi of s is less than or equal to n plus m. Right, depending on the values of the f's and the g's, at most it'll have degree n plus m. Okay, and so our problem, I'll write the problem and then we'll do it the solution next time. Pole placement problem. Sometimes I'll write it as P, P, P. Is given P. And n plus m desired closed loop poles. Which I will write as lambda 1 to lambda n plus m. Shouldn't see this. Yes, 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 yes. Sorry, that's a typo. Sorry about that. Thank you. So given a plant, given desired pole locations, using the stuff we just talked about, design a controller. So these guys will be in some good region. Find C of S so that the roots of pi of s equal lambda 1 to lambda n plus n. All right. So that's the problem we're going to solve. And basically what it's going to come down to is you have to have enough tuning knobs on your controller, enough gains to tweak, right? So in other words, as long as m is sufficiently big, you can always solve this problem. In other words, as long as you have enough gains that you can tweak on your controller, you can solve this problem. All right? If we run out of time, we will solve this. Well, we'll present the solution, and then we'll do some examples next class. All right? Have a good rest of your day, and I will stick around for a couple minutes before heading off.